My name is Niels Larsen. I have the pleasure this morning of introducing our two speakers. And it's quite, the two speakers represent very different approaches into the field. Mr. Germaas, who is speaking first, represents the on-the-ground application, so to speak. He represents NCORD, which is a consortium of the 20 largest construction firms in Europe. Their group that does research and development to improve their work. And I'll talk a little bit more about it in a second. But Dr. Grtzel, Michael Grtzel, who's the second speaker, is coming from the theoretical end, if you like. And of course, we need both to move ahead, and eventually the theory meets the practice, sometimes very happily, sometimes not. But I find it quite interesting to see this juxtaposition of theory and practice-driven research. We will start with Germaas and a little more about NCORD and Mr. Maas. Mr. Maas is Director of Strategy at Koninklijke BAM Group, and he's also a professor at the Department of Architecture, Building and Planning of Eindhoven, in addition to acting as the sort of focal point for NCORD in their work. I saw they had a meeting here yesterday, and I hope it went well. One of the interesting things that Mr. Maas showed me was this little brochure, which is available on the tables on the side. It is an outline of their sustainability charter, which will form the sort of structure for the lecture of Mr. Maas this morning. And obviously, it's quite significant if you can get the 20 largest construction companies in Europe to agree on a way of working that reduces their environmental footprint and improves the sustainability. Mr. Maas will be speaking about 30 minutes, or a few minutes less, and then we will get on to Dr. Grtzel at that point. We're also connected on the internet. There may be some messages coming in on the line here, and so hello, internet people, wherever you are. There were about 200 yesterday, apparently, in Mexico and various other countries, so that's nice that this kind of long-distance connection can work. So, Mr. Maas, I will hand it over to you.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen in the room, and good morning or good afternoon, ladies and gentlemen elsewhere in the world. Or good night, perhaps, you don't know. It's a pleasure, it's a great honor for me to be here in this 11th World Sustainability Building Conference about improving the quality of life, about mitigating the effects of climate change, and about making new businesses. The question that I first have, I'm mainly from the industry, partly from the academic world, but what's your background? Where are you from? And I can't ask it, people from Mexico or New Zealand. Perhaps they can send an SMS and then we know what kind of people are looking to us. But raise your hands who is from the academic world. Ah, good, great. And who is from public services, public governmental agencies? A lot of them. Thank you. And who is from the producing industry? Also many. Thank you very much. Well, I'm talking to you from the background of the industry. Anchored, as the chairman said, is representing the leading construction companies in Europe, and we are the producing part of the industry. And our sustainable charter has the aim of improving quality of life and mitigating the effects of the climate change. And our network, these are our members, and if you see at the left side, also from these Nordic European countries, YIT, Uponor, Skanska at the bottom, NCC, and at the right side, Consolis, the representatives of the Nordic European countries. And our aim is together initiate, stimulate, and do research and development, but always with the aim of coming to innovation. Innovation that really can support our clients in their needs. We are members of society. Our employees are members of society. Our employees are ordinary people living in the neighborhoods of our cities. And that's why we like to take up our responsibility for society. So responsibility by development of a charter that can take our companies with commitment from innovation and give a major contribution to a more sustainable world. Last June, we gathered in Amsterdam to sign a charter. And like the chairman of this meeting said, this is the charter. You can find it there on the tables. If you leave the room, you can also stand up and go to there and take one. I don't know if I have that many copies enough for all the people in the room, but nevertheless, then you can come to us and we can send you later on other examples. In our charter, we integrate the sustainability principles into our business and innovation strategy. And finally, to come to a greater added value for the built environment. Like this example of a refugee in the mountains of Austria, built as a passive house far away from our neighborhoods and our cities. We promote best practices amongst our partners. We will like to take innovation to our sites. And this is the charter that our members have signed. And I'm happy to introduce the content of this charter to you with some examples of sustainable innovations. The first item of the charter is, what are we doing? Well, we are focusing on research, development and innovation and specifically realizing sustainable innovation. A first example is this one. Tubes for tunnels, tubes for metros and things like that. But you also can use them to harvest the geothermal heat from the earth. Another one, the second statement in our charter. Build on our knowledge of measuring our own sustainability performance. In accordance with the Global Reporting Initiative, we developed a protocol to measure, to report, and to compare the CO2 emissions of our construction companies and our construction processes. And this protocol is now part of the GRI system. The third item of this sustainability charter: eco-efficiency in our solutions and products through the life cycle. How do we do that? Well, an example of this is this one of NCC, low temperature asphalt, to decrease the CO2 emissions by up to 30%. The fourth item of the charter: support and influence our clients in adopting life cycle opportunities. This is the point of the aging society. Aging people have to act in their daily life, and sometimes people have diseases, can't do everything what they like, and that means they need additional support by technology, by another built environment to enjoy their lives and to live their lives. Well, this kind of research takes us to improving the built environment and to make the built environment sustainable also for an inclusive society. A fifth item in our charter: foster the well-being of our employees. Health and safety of the employees, of our employees, and also of the employees of our subcontractors, as well as for the community. One of the members of our network developed RFID systems to improve the health and safety issues in civil works, and specifically in tunneling works. You can find it on their website, the details. A sixth statement in our charter: demonstrate social responsibility by promoting initiatives that show respect for the people and the local communities associated with our business. And what we all know is construction usually go hand by hand with a lot of noise. Okay, Bouygues developed a tool to simulate the noise impact, and this noise impact includes our construction activities. Well, this is a nice tool to communicate with the neighborhood what happens on site and eventually how we can adjust our work on site to the needs of the neighborhood. Another example is this one, to demonstrate respect for local environment. This is a development of a system for monitoring the emissions and monitoring the development of an ecosystem in national parks. Okay, coming to another item, a more abstract item: elevating the ethical standards in our work, elevating the ethical standards in our companies. We like to conduct our business with high ethical standards in dealing with employees, customers, suppliers, and the community at large. And how do you do that? Well, we discussed 2 years ago, 2.5 years ago, for the first time this item with Ernst von Weizsäcker. And a half year ago in Amsterdam, we discussed this ethical item with Ivo de Boer. And both are former chairman of the United Nations Climate Change Conferences. And we discussed with them the impact of corporate social responsibility and sustainable behavior for our members. An 8th item is the stakeholder engagement. We like to engage our stakeholders and independent third parties in the way we act in our projects. And a good development to take this up is that we use the building information modeling we can use, and we are developing as anchored members virtual construction to attract all stakeholders to our activities. Transparency, always an issue in construction. We like to be open and active in our communication, and we like to help construction companies and other organizations in our supply chain to implement sustainable practices. And there are a lot of internet tools to communicate with our clients and to communicate with the neighborhoods, measurements about CO2, about waste, water, and other KPIs, but also sustainability management, measurements and reporting tools so that we can communicate this with the neighborhoods and with partners in the supply chain. And finally, the last item in our charter focuses on the value for our stakeholders. We introduce and we are introducing tools as BIM and lean management to focus on our employees, on the largest and on the value of the, we are focusing and introducing tools as BIM and lean management to focus our employees on the value development for our stakeholders. And this is introduced, by example, in London by the development and design and construction of the London Heathrow Terminal 5 building. And how do you come to action? This charter is a first step, and the second one is come to an action plan. And this action plan, there is a lot of wording, but focus on the bold ones. This action plan is focusing on the improvement of our sustainable governance, on sustainable development through the life cycle, on the working, the health and safety on site, on creating a great place to work, on having good relations with our local communities, raising our ethical standards, and finally come to value for our stakeholders. And I'm talking about this network. This network of companies made this charter, what I just presented to you. They signed this charter and are committed to it. And the network, as well as the members, strive to have an impact. And they can have an impact. Together, this group of 20 European top contractors, I'm presenting here 15, because the slide is not big enough. They are in the top of the European construction industry, as you can see in the first column, but they're also globally in the top of the construction industry. And together, if you see the last column presents the volume of the new contract that they acquired in 2010. In the last column, together, this network of construction companies acquired 275 billion US dollar as production volume in new contracts. And this huge volume represents the impact that our members can have and will have in construction in large sites and at small sites, in simple monodisciplinary projects and in more integrated multidisciplinary projects. They will have an impact to implement the innovations that are necessary to reach the aims of this charter. And finally, this charter will bring us to a sustainable performance, Mr. Chairman. Thank you.
Okay. Yeah. So, hello again. That was a nice, clear summary of a sustainable development approach. And now we turn to more theoretical issues. Dr. Michael Grtzel, who is director of the Laboratory of Photonics and Interfaces at the École Polytechnique Fédérale de Lausanne in Switzerland. And one of the several reasons he is here today is because he won the Millennium Technology Grand Prize in 2010, which is quite a nice prize, 800,000 euro. I hope you haven't spent it all yet. It was for his invention and development of dye-sensitized solar cells, also known as Grtzel cells. We're going to hear a fairly long presentation and in detail on this. I must say I became intrigued by the reference to mesoscopic physics. So I did my research on the wiki site, of course, to find out what mesoscopic was. And it's interesting. It's a scale in between something like in between viruses and bacteria in size. And these are materials that have quantum behavior or quasi-quantum. This is what I will be very intrigued to hear, where they fit between classical physics behavior and quantum physics. Anyway, I understand nothing of it, but I think we will all understand a lot more after this lecture on the development of these solar cells, which didn't come overnight, because first attempts from Dr. Grtzel's team was in 1988, and it's gone on from there. So fundamental improvements take a long time to effect. Dr. Grtzel?
Morning, it's a pleasure to be here. Thank you, Niels, for your kind introduction. And I'd like to thank the organizers for inviting me to this meeting. Building integrated photovoltaics has been on my heart and mind for a long time. And so today we will be presenting some innovations in this field. And so one of the fundamental elements in these innovations is the mesoscopic solar cell. As you can see from the first slide, these solar cells are not the common kind of black-looking panels on the roof of a building. These are solar cells that have features that are uncommon to the competitors. For example, the right cell is a module. You see transparency. So color transparency are options we have in this technology. I should actually mention the mesoscopic. The name mesoscopic, as our chairman mentioned, is to define a size, feature size. And so the the feature size is 2 to 50 nanometers. So these cells have at their heart very small pigment particles, titanium pigment particles. They're of the order of 20 nanometer size. And they are loaded on the surface with a dye molecule. And so what that offers you is a choice of the dye. You can get different colors. You can print those films. See an example from Sony Corporation here on the left side. This is a solar cell. It looks like an artist kind of design, but no, it's and actually Sony just presented in Lausanne. We had some exhibition there, an enlarged version of this panel, which they call Hanamoda. It's a flower wall. And so these cells can be made into elements, actually, that could be integrated in building walls. And just think about the beauty aesthetics of this. Not to forget the beauty of the young lady that holds the cell. And so, the technology is different. It's a new paradigm. And what I wanted to do this morning is to familiarize you with this new paradigm. And first of all, I will give you a brief introduction and present the technology. But it's not a theoretical talk. Don't be afraid. Quantum size effects, yes, we could talk about this, but you would be terribly bored after a while. So I just mentioned, yes, in this size domain, there are quantum size effects, which means that the optical properties of those small pigment particles, they are not the same as for bigger size particles. But that's a side effect that allows you to tune color. And of course, people use that. But in this case, actually, we use dyes that are adsorbed onto the surface of these white. The pigment is actually white. You can't see the particles. They are too small to be seen. That's why we have the transparency. And we'll see several other examples during my lecture. So the first part, I will tell you about the principle of the cell. And then I'd like to show you some building integration applications. So let's get this going. Well, we all know that we have a problem in the energy field. Demand will double in the next 40 years. That's a conservative estimate. Today's consumption is about 15 terawatt. That's a power consumption. It will go up to about 30 terawatts. And so the question is, where do we take that extra power from? Well, certainly not from the oil, which is coming down, actually. And all the fossil resources, they have the problem that they produce greenhouse gases, and not to speak of pollution. And then we had this terrible disaster in Japan, which was a huge setback for nuclear. So one has to look into renewables, and that's the conviction of many people now, that the quest for renewable energy is, of course, one of the main challenges that we are facing in the next decades. And so we see here some of the traditional, that's photovoltaics, but renewable is not only photovoltaics. Wind, solar is renewable. So solar means wind, hydroelectric, biomass, all this is solar. And also concentrated thermal power. So thermal solar power is also solar, of course. Photovoltaics is a part of the solar family. Here we see classical silicon panels. We see the dish in the Himalayas, cooking food. So this is more of a traditional way. We have, these are now these cells that we developed. So they see that in Japan, Fujikura, these are panels that are used along the road, along the highways to collect solar power. That's the idea behind it. And also, you see some modules here on the roof in Jerusalem. These are outside outdoor tests that have been performed to see how these modules fare in comparison to classical or conventional cells. I'll tell you more about it later in my lecture. So the work done is performed is at the EPFL, École Polytechnique Fédérale de Lausanne. This is our campus, Lake of Geneva. I'd like to thank the members of my group. I'd also like to thank for funding from these various organizations. And last but not least, the Millennium Prize was, of course, a big boost for us and has helped us to further accelerate the development of this technology. So the PV is on everybody's mind, but the contribution today to the total energy supply of the world is very, very small. It's only 0.04%. But yet, this business is already a $30 billion business today. So we're talking about something like 15 to 20 gigawatt peak power installed every year. And so that's that kind of business, at least $30 billion business. So just think about it. If you go from 0.04 to 4%, what the business will be, it will be a $3 trillion business. And if it becomes 40%, well, then it becomes a huge, almost the whole world GDP, $30 trillion business. So this, I'm not saying that the 40% will be reached. I have my doubts, but perhaps eventually. But in the next 40 years, we have to get to the terawatt scale. And so we have to get to the percentage numbers, not a fraction of a percent. And so there's a huge growth also behind this, a huge potential industrial growth, which has averaged about 20% per year in the last couple of decades. But to get to this scale, we have to get to unsubsidized conditions. Today's PV market is in a turmoil because of the problems with the subsidies and feed-in tariffs, and they go up and down. And so at the end, if you want to scale up by a factor of 100, nobody could pay the subsidies anymore. So that scale, you have to provide a competitive price electric power by PV. And so that means, evidently, there has to be cost reduction process. These are trivial arguments. Efficiency, stability. What I like to mention is the short energy payback time. That's something that people sometimes or often ignore. In other words, the time it takes for the energy to be recovered that you put in making the cell. And so life cycle analysis has to be performed, and that has been done, but the figures are not always clear. So let's just say the following. For silicon panels, it's about 2 to 3 years in favorable conditions, that is, at the latitudes where there's a lot of sunshine. For the dye-sensitized or mesoscopic solar cells, definitely lower. We don't have any high temperature process. We don't need 99.99996 nines in the solar grade silicon. It's a high purity, high temperature. So these are energy intensive processes that use up a lot of energy. And so if you have 20% growth and say 2 to 3 years payback time, actually the growth will consume more energy than you make with the panels. And so that becomes an energy deficient industry until you get up and you don't have to grow anymore. You have reached your limit, and then becomes a net surplus. But so these kind of arguments are rarely been made, and I think they need to, because after all, the balance has to be clear for the next decades. So energy payback time and also the environmental impact. Some of the thin film panels use cadmium and tellurium toxic materials, and so the recycling is a real issue. if you want to scale up from today a factor of 100, there will be solar panels everywhere. So we have to know how to take care of these once they run out of performance and operation. So here comes my theoretical slide, Chairman. And I like to refer to the man, Albert Einstein, who is, of course, the one who explained the photoelectric effect. But it's a very simple effect. As a matter of fact, I think many of you could read that paper of Einstein I just showed you and understand it. It's not so difficult. So what happens in the Mesoscopic solar cell is that you use a molecule, a sensitizer, as light absorber. It's not a silicon material. It's not a PN junction. But it's a molecule that absorbs light, or a quantum dot, as in the quantum semiconductor dot. But we're focusing on the dyes today. And so the molecule is at the limit between two materials. One is conducting negative charges, electrons, n-type. And we have electrolyte or some other conductor that moves the positive charge. So very simple. You have the dye or sensitizer just as a sandwich in between those two materials. When light hits the dye, it becomes energized. Or people say in the language, professional language is the dye becomes excited. So it's like when we get excited, we're energized. So the dye, the excited dye, will then be able, because it's gained all this energy from the incoming photon, to release an electron. That's a photoelectric effect. So it ejects an electron in this particle network, actually. That's a particle network. It's the titanium material that conducts electrons. And, well, then the sensitizer, once it loses electron, it has a positive charge. So we have to replenish that. And so we have to move the positive charge out. So the sensitizer do both electron injection and positive charge injection. Sometimes also this is called a hole. Electron hole is a positive charge. So the physicist says a hole, but it's really the positive charge. And so that's all. We're making just electricity from a molecule. And that same process happens every day out in the sun in the green leaf. It's just that the chlorophyll that produces these electric charges is acting the same way, but the charges are not coming out of the leaf as electric current. You haven't seen that, I don't think. So what happens is that very quickly on a very small length scale, nanometer, these charges are used up in redox reaction, in chemical reactions that produce our fuel, from CO2, the sugar, and oxygen from water. So electrochemical reactions in the plant convert those charges into fuels. But we are taking deliberately, we can do that too in our cell, but at the moment the most prominent configuration is the photoelectric configuration, where we use these charges to produce electric current. So that's all I will say about the functioning of this device. Just to illustrate, this is, of course, the famous paper in year 1905, where Einstein has postulated. He's very careful in the title. I see he uses the word heuristic. Who knows in the audience what heuristic means? Please. A few people, yes. When I ask my students, they don't know. And so it's a kind of a very nice way to hide what really is behind. Heuristic in this context means it's by intuition. It's not really a strict rationale behind it, physical rationale. It's by intuition. So one more time, we excite. Remember the excitation, and sensitizer gets excited. It gets more energy from the photon it absorbs. And so it's now in a position to release a charge in these TiO2. TiO2 is titanium. It's a white pigment a lot of people use in toothpaste and on walls. It's totally anodyne. It's cheap, available in large quantities. It's harmless. So, but the key point here is we're using a very small feature size so that the surface area of those films is huge. It's about 10,000 times, at least 1,000 times bigger than the projected area. And so that makes it possible to capture the light. If we had the chromophore or the sensitizer just on a flat surface, it wouldn't absorb any light. So it would just, well, very little. And so that couldn't be a photovoltaic device. We need, for the light harvesting to be efficient, we need this third dimension. And so I just indicate those particles here. So electrons are released into those small particles, and that sets up a charge separation. A positive charge remains on the S, so we have S plus and electron. But then, as I said, we have to regenerate the sensitizer. So there's a shuttle that does it. Just think about the shuttle that picks up the positive charge, molecular shuttle. And so that now we have the charge separated. One positive charge is on D plus, and the electron is in the particle. So that sets up a voltage. Any charge separation sets up a voltage, and that drives the photovoltaic cell. So that's it. And here's the first paper that reported on this particular embodiment was in Nature 1991. And you see the mesoscopic particles. Very small. It's a network of particles, and size domain is mesoscopic, in other words, 20, 30 nanometer. So these particles form a network, and one of the issues that you have when you use a system of this type is that people are worried about whether the electrons that you inject will make it through these many, many particles and be finally collected as electric current. And so the issue we were facing at the beginning, at the outset of this development, was we had skepticism. A lot of colleagues thought, well, yes, the initial step, the photoelectric effect, we believe that's Einstein's theory, but how do you collect those carriers? It's a disordered network. There's no field, electric field, that helps you in a collection. And so that was the challenge is really to convince our colleagues that with this three-dimensional, the first three-dimensional junction solar cell, that it's possible to do that. And so you can also see on the right side, you see there's another transparent glass panel. It will be important for the building integrated photovoltaics because our cell is the only one that can make panels of glass you can look through, and different colors. Could even make a glass panel where you have no color and still produce electric current. So how would you do that? Well, you would need a near-infrared sensitizer that leaves a gap in the visible. These exist. It's not a miracle. So there are lots of options here. The red color appears a lot because in the initial part of our studies, we used some ruthenium complexes as dyes, and they had this red color. But nowadays, if you want a green one or yellow or blue, just let me know. No problem. So, so this is then the device, two glass panels. They act as current collectors. Glass usually doesn't conduct electricity, but there is a very thin film of conducting, so-called transparent conducting oxide. It's called TCO. You have this also in thermal, the insulating glass. It's a coating that kind of puts a slight tinge interference color under the glass. This coating is conductive, and so you collect the electric current through that coating. And so you can make a cell that has 2 glass plates. Just, if you like, it's like a window. And it's in between the 2 glass plates is the photoactive material that produces electric current from light. So that's also something very, very important when you do cost calculations. If the photovoltaic cell is part of a glass facade, well, the glass you will have to pay anyway for that glass. And so putting the conductive coating is not that more expensive. It can be done in float glass fabrication lines. And so it's really an added value you have. You add value add on to the glass that can produce electricity. At the same time, it's colored. It can be beautiful, aesthetically pleasing. So that's the selling argument, one of the selling arguments of our technology. And so we have different ways that this embodiments come with electrolytes or solids. I think I can move on. This is a typical embodiment. The dye. I show the dye structure here. This is the red dye you just saw. We have this paste, which has the mesoscopic particles dispersed. So the paste can be printed. It's very simple to make those cells. And then you have a ionic liquid. This is a preferred electrolyte because it has a very low vapor pressure, and it's not evaporating, or the leakage problems are relieved. So a lot of the practical applications today use those ionic liquids. These are amazing materials because they are salts, but liquid down to -50 or -80 degrees. That's the magic of chemistry. It can make a salt into a liquid and remain a liquid even at low temperatures. And so, final slide on the introductory part. So we have this very rapid photoelectric effect. We have to regenerate the dye. And the collection, well, do we collect those carriers? I mentioned that problem. And so well, it's very simple. If your collection time is 100 times faster than the recombination time of the negative positive charge, they love to recombine with each other. They're energized, so they like to release that energy, recombine. So you have to keep them apart, and long enough to be able to collect the carriers. Long enough means collection time has to be 100 times faster than recombination time. If you take that message home, you have really understood the fundamentals of the solar cell. And so we have now in the so-called standard reporting condition, which everybody uses in PV, it's a sun at a certain angle, 43 degrees. It's called AM 1.5, air mass 1.5. 1.5 being the path length of the sun in the atmosphere. 1.5 means 1.5 times longer than the vertical path length. That's an average that people use, and the sun spectrum changes, so we have to use that particular sun spectrum. And then it's normalized to 1,000 watts, and then per square meter, and then people do measurement at 25 degrees. Well, that's not a natural condition, because when you put a full sun on the cell, it will go up in temperature. So here's something that is a little bit artificial. And it works in favor of silicon PV. But we don't have the temperature problem in our cells. We can do the measurement at 50 degrees. So that works out to be an advantage in real outdoor conditions. And so we have the stability and development. I mentioned already these things before. So a lot of research going on. I don't want to go into details on the research. The main goal is, of course, to improve these. Efficiency could be, for any photovoltaic cell that has a single junction, is up to 31%. So we still have a way to go to get to the limits of this technology. And so one of the reasons you want to move further in the red, this is today's slides, they absorb below 800 nanometers, is that you get more current, you collect more photons from the sun. This dark part is a solar emission, the AM 1.5 solar emission. And so you want to capture up to 900. That would be ideal, to capture all the photons up to 900 and get the maximum voltage out. And then this product, voltage times current, would be the best you can get. So not better than to give you a 31% on the left. And you see also the many color options we have. And so I'll show you later a few examples of these so-called JV curves, where you plot the photocurrent. This is measured in milliamps per square centimeter, and against the voltage of the cell. And one voltage, you have the maximum power. The product of voltage current will be the maximum. And that's where the efficiency is measured. You measure the efficiency at a point where your output is maximum. That's normal. And so, as you can see, over the years, we started with the red curve. We have gained a significant red response, and just changing the chemical structure of these dyes, ruthenium, go to a little bit different structure. We won't go into chemistry now and the rationale behind this, but recently in Japan, the group at Tokyo University, Professor Segawa's group and Uchida's group, they came up with this dye that really looks black. I mean, it captures all the light below 1,000 nanometers. It's like a molecular silicon cell in a way, and very high conversion efficiencies. What we plot on the left is the conversion of incoming photons to electric current. Incoming, so we count the number of photons that strike the cell, and we count electrons that go out, and that ratio, if that's 80%, that means more than 80% of the photons of this particular wavelength will be converted to electric current. So these very high numbers are, of course, also achieved by silicon photovoltaic cells, but they need 300 micron thick films to get to this. We can use 100 times less, and we use a molecular dye. We don't have to invest in all that silicon to get the light harvested. So there have been some improvements in the chemistry, and today's best cell actually looks green. Isn't that amazing? I mean, we have used a porphyrin sensitizer. We developed together with the group from Taiwan, Dr. Diao and Professor Yi's group. This is a chemically engineered sensitizer that has now shown the highest efficiency. It's between 12 and 13%. And it has this beautiful green color. Just think about it. You could make a building that looks green. Wouldn't that be nice? Some people love green colors. And so that's the latest development. And this just shows you the structure of this dye. And also we can make the cell black if we make a mixture of dyes. But the red curve would look green. It has a little dip here in the collection efficiency, in the light collection efficiency, so that light passes and that gives us a green color. And so we're back to nature, because nature uses a very similar sensitizer. We go back, show you, in the natural chlorophyll you also have this tetrapyrrole structure. It's a close cousin of our dye. Simply, here we have a donor, we have accepted. This is all engineered. I don't have the time to go into the details. It's all engineered so that you get not only maximum light harvesting, but you get also very high voltage out of the cell. And so what happens, for example, these two groups are added on to the dye to prevent the electron from leaking back out once it's injected into the titanium pigment particles. So these are insulating groups that keep the charges apart, and hence you get a higher voltage. And so you can also see that in natural photosynthesis, you wouldn't get a spectral response like that. It's far more sluggish. The absorption is around 650. But by using this donor acceptor concept, you get a beautiful response across all the visible, starting from 720, go up to 80, over 80, 90%, over 90%. It stays up there. And this drop in the UV just comes from an anti-reflective coating. Anyway, in the UV, there are not many solar photons. And so the high voltage, that is what the dye is not better in the spectral response compared to the earlier ones I showed you. The molecular silicon dye is actually better than the porphyrin, but get high voltage, and that counts. This is over 900 millivolts. So this was a new record in the mesoscopic solar cell field to get these high voltages. And the reason why we get high voltages, we followed on there was a recent breakthrough that was actually a Swedish colleague, Professor Anders Hagfeldt, who came up with the revelation that one could use these cobalt complexes instead of the iodide, triiodide. And so that provided means to move the voltages up. And so we now look at some of the stability we can run with these panels. These are now panels that the level of efficiency is 8%. Panels always have a lower efficiency than the laboratory cells. The highest panel efficiency we have is the standard condition. That's all standard, measured at 25 degrees. We are also covering the back of the cell with a black cloth. Our cells have a bifacial light scavenging. They capture light from all angles. And so if we uncover the back, we can capture more light, but that's not allowed in the standard test. So the present module efficiency we achieve at a standard test is 10%. And that's the maximum. But that's good. I mean, it's competitive with some other thin film technologies. It's lower than silicon, but I should say that in the outdoor, we make up for the difference. And I mentioned some examples before. So, so the 85 test, 85 degrees centigrade, 85 humidity is very, very critical. You do that over 1,000 hours, just imagine. Keep that cell at 85 degrees and 85% humidity for 1,000 hours, that's 6 weeks. It's a strenuous condition. Just think about if you had to go in a chamber that was at 85 and 85 humidity for 6 weeks, how much would be left? So these cells are sustaining that very harsh condition. And under light, we have no degradation. We have very stable behavior. Here's a heat cycle, minus 40 plus 90. Go back and forth 200 times. So these are conditions that are also applied as standard to show that you have something that is stable under outdoor. And of course, in the building integration, we need to have that assurance for the client that the cells won't die within the next month after you install them. And so the reason for this very high stability is these ionic liquids. I won't say much about it. They're actually, these electrolytes are solidified by adding SiO2 nanoparticles, and I pass over that. But you can see here the very good stability. Here's one test over 4,000 hours under light soaking at 65 degrees. So if we use those new solid electrolytes, we get very, very stable cell output. So that brings me to the second and final part of my presentation. Actually, this is the part that should be of most interest to this audience. What I have given you so far is just some background information on the mesoscopic solar cells. Let's see where we are strong and where we can be competing with the existing PV cells, conventional PV cells. So the ease of building integration, I will show you that in a minute. So it's the reason for that ease is that you can make the glass panels and skylights and facades. Actually, the École Polytechnique is setting up a new conference center near to our campus, just next to it. And one of the walls will be equipped with the dye-sensitized panels to show that the technology to the convention people that will come for the conventions. So that's, that has to be there at year 2013, because that's when the first conference will be held in this new conference center. So building integration, very important. Transparency, multicolor option, yes. That's something unique selling proposition, because other technologies don't have that. Well, there are transparent PV panels, but if you look carefully, they are made in a way that this part of the active material is scratched off the glass, or just some dots are printed, so that at the end you only have a part of the glass covered with the photoactive material. This is not what we are talking about. We are talking about films that are translucent, and the whole area is photoactive. And so, so here are some panels again, multicolor option. The dye determines the color of the device. Flexibility, I show some examples later. And this is again a Japanese setting with a very nice Japanese lady showing the cells. These are actually for indoor. I should mention to you that I think time has come for photovoltaics to also be integrated indoor, not only on the building outside, but for example, these lamps, these are again Sony products. They're called Hana Akari. Hana is flower and Akari is lamp. I learned those two Japanese words. I told you about Hana Modi before, so this is Hana Akari. Flower lamps. And the flowers is on these panels. These panels, all these panels are photovoltaic cells. You wouldn't think that, but that's, just believe me. And so the light is captured from outside and inside. So it's a bifacial cell that captures light ambient. It doesn't have to, you don't have to carry this lamp out in the sun to get some light back so that you charge your batteries. It's ambient. It's working on ambient light. And so the ambient light would use enough electricity to charge a battery, and then you, with a LED, you bring the light back. And you have an autonomy of at least 7 hours from a typical daily exposure. So at night, you're free. You never use a plug for these lamps. And so I think we will see much more of that. There will be actually a revolution coming where the photovoltaic systems become part of the interior space. You could make walls, furniture. You could do all sorts of things with that technology to produce electric power from ambient light. And there also, I have to mention to you that the efficiency is very high. A typical ambient light condition like we have here, we can get 30% or even more conversion efficiency. It's, of course, less light coming in, but the fraction that is converted is much higher than the total. We use solar light where a lot of the infrared photons that count as energy are not captured. well, there's just some small gadgets I show you. And so, so this is, these are some of the elements that have been made in the wall. I mentioned that to you before. Hanamado, I think is the name. Here we have the largest screen printed panel. And if you see that in a real module, you'd be amazed. It's just very beautiful. The picture doesn't do justice to the beauty of the module. And to actually, Dr. Andreas Hinch is behind this technology. You see him across the film. And so this is a 60 times 120 sized module. And it would fit very nicely into the facade, which is being built at the EPFL campus for the new Congress Center. And so this could be stacked up to 20 meters as you need. Also, the Grtzel Tata. Tata was mentioned as one of the companies in the previous talk that has signed up to the sustainable building concept. And so these, they don't look quite as nice as the previous panel, but they are used to cover steel. And so a lot of buildings are warehouses, and they use steel as a construction material. And so you could put the cell, to paint the cell on steel and make it into a photovoltaic device. And so this breakthrough was actually announced this year. This total area is 1 square meter. And so the idea is to bring the cost down and use the steel cladding as a current collector. And so, so that's again this project, and we have the Tata Grtzel production chain in Wales. Here's one picture I had in my abstract on building integration, some panels in Australia. This is actually Nina is from Aarhus. She has done a very detailed analysis on our technology, and she has confirmed it's the only one that is around that can make those transparent windows and electricity-producing glass facades. And this is one building in Australia, bigger project. This is smaller. Rooftop applications are, of course, possible, but I don't think it's the first market that will be addressed. These panels are very often mounted to do outdoor testing and see how things work out and to gain experience with the efficiencies we achieve under real conditions outside and also stability. And so this building is a very special building in Nagoya. So very useful, I would say. If you are in Nagoya in the city park, please use that opportunity to visit. And so, well, what comes out of these tests is that the harvesting of the DSC is a green curve. Just take over a whole day of sunshine. Okay, so what you see is that the dye-sensitized cells pick up much earlier the light energy from the sun, and also they remain active later in the day. Why is that? Well, I mentioned the angular dependence of the efficiency is very low, and so that's an advantage when it comes to outdoor applications. And here we are not even counting the light that comes back from the albedo, from the backside, or from inside a room that would be reflected back onto the window. And so that's in facade orientations. The relative energy output could be 75% higher than when you integrate this power over the day. You get the energy, and that you see there's very significant differences when you look at the integral over these curves. So that works to our advantage. Also, the fact that here we see some of the competitors. If you are in an area like this, is I think a tropical area where there's a lot of diffuse light. The bluish part is diffuse. And so lots of clouds, well, the efficiency of silicon panel will drop. So they're not performing at the rated efficiency. But in contrast, the dye sensitized, they go up, they laugh. Cloudy weather. Finland would be a very nice opportunity for these cells. And so also temperature is a bad thing. When you heat up the normal conventional cells, the degrees, from 20 to 60 degrees, they will lose about 20% the efficiency. In the dye sensitized, actually, it's very flat. There's no, it's a small increase up to 60 degrees, and then it slowly comes down. So outdoor, there are conditions that are favorable. And what that means is that at the end, we have, this is just for the silicon, just focus on that, the levelized cost of energy. That's what people are interested in. What is the US cents per kilowatt hour? And so that's a calculation. These are programs that come out of NREL and comes from industry. And it shows that even though the efficiency of there was a 7% panel, which was compared to a 12 or 11% silicon panel, so there was almost a factor of 2 in the rated performance, and outside the price per kilowatt hour is actually lower for the green part, which is the DSC, especially if you go to Eastern or if you go to orientations where you have a lot of diffuse light, then of course we see the advantage. So the conclusions from these outdoor building experiments, applications are that well, the technology is becoming more and more attractive for commercial applications. We have, despite of the low rating under standard condition, we have outdoor advantages. And so that leads to a very low level of the price per kilowatt hour. That's finally what's important for the client. He wants to know how much does 1 kilowatt hour cost. The client is not interested in a peak watt rating. Doesn't know what that is. So now I have one small added part to this lecture, the final part, that deals with the flexible cells. So this technology can also be made into flexible cells. Lightweight, can be carried. And one plant is in operation in Cardiff, Wales. And it's now already producing several megawatts of power on the flexible. The windmill is providing the energy to make the cells. So you can imagine the footprint, the carbon footprint is very low for this technology. And so that's in Cardiff, Wales, and you see the 2.3 megawatt wind turbine power. It's too much for the plant, so some of the electricity is being sold to Wales, to Cardiff. And so that's a very nice setting. I mean, you can also see the cloudy condition in Wales. And of course, as I mentioned, that's particularly favorable for our technology. And so, so these are now roll-to-roll produced on plastic or metal foil. And see here one of the production lines. And then you just cut with the scissors the cells. And you can use them for example, here we have a keyboard. That's all sorts of applications that are in the ambient or outdoor. And so here's for ambient applications, you see the keyboard. Some of you might know this gentleman. This is German president Christian Wolff, and this is, in Switzerland, we change every year the president. So people are very careful in Switzerland with their presidents. And so, so this was Doris Leuthard. As at the time when the visit was, we had a big tax issue with the Swiss and the German. But you see how the cells, how the smile came back on the faces. And so that was a very nice present with the German colors and Swiss flag we provided to those visitors. And we see also the integration. Logitech is powering computer peripherals. See now part of the amplifier is now photovoltaically active. You could make a table photovoltaically active. You can integrate those light waves or glass elements in a lot of ways also indoor. So that could be sensor applications. There are many applications that are looked for. A bag is being sold. You can go on the G24 website and power the battery, and then you can use that to power your computer or a phone or a lamp. So in India, this same bag comes at a much lower cost and price. So they see the ladies how happy they are with that bag, because they love to carry those bags all the day, and so all the day they can capture sunlight. And then at night, for example, you can get over an LED a light bag. You don't have to use a kerosene lamp anymore. And this was the latest for tsunami victims. I just mentioned that because there was no electricity. So the ambient light application, again, here with a more solid kind of cell. And I was very delighted to receive one of those lamps from our Japanese colleagues. As the technology has made a contribution to alleviate the painful experience that our Japanese citizens had to face. Just look at this couple, how happy they are having a lamp. I mean, you go down to really the basics if you have no electricity. And so, of course, cars also. It will come that we power cars here. The latest smart car will be exhibited. These are dye-sensitized mesoscopic solar cells. So I finished by showing you for the flex cells one application that is, again, on a larger scale. It's in hotels where the MGM has placed an order for equipping all those windows with the blinds that have the flexible cells. And so the room gets very hot in Las Vegas, so they want to blind the sun out. And these blinds will at the same time produce electric power to supply to air conditioning. And so we have been witnessing a good growth in this technology, and I look forward to further growth. It's very important to educate the young people. They have to pick up this slab, and the next 40 years is a challenge. So we need infatuation of the young generation to come in and help with solving some of the energy problems. And so we start very early. We have these experiments where we make cells out of natural dyes from blackberries or from cabbage or tea, and that has helped a lot. We also go to younger generation, and this with this slide I like to finish. So it's possible to even for school children to make those mesoscopic solar cells. Well, I have taken you through a long voyage. It has taken 1 hour, so I hope you didn't fall asleep. And so, if so, it's time to wake up. And it was a pleasure to be here. It was a pleasure to talk also to the international audience about this exciting new technology. And I'd like to thank again the organizers for having invited me, the Technology Academy of Finland for selecting me as a prize winner last year. It has been a tremendous honor. It's fostered our technology. And last but not least, I'd like to thank you for your attention.
Well, that was a real grand tour, going right from theory to practical applications. I must say, it's got a lot of implications for changes in architectural design. I'm an architect, and I can see that you need to twist your head around a little bit to really grasp the full implications of this. We are a little bit ahead, so if you have any questions or issues you would like to raise about this, we have some comments from the land of the internet. Truly amazing, yes. Yes, very interesting topics right from the beginning of the day. Well, that's a good positive outlook. Are there any specific questions anybody would like to pose here? Sir, are you? Maybe that's going to be a question, yes, or a comment.
Thanks for the interesting talk, Professor. I'm interested in the last part of your presentation regarding experiments that school children can do with organic dye. From very simple research on the wiki, it mentioned about the toxic substance that's used in the dye for these cells. Have you resolved the toxic problem, and is organic, non-toxic berry-based dye something that's readily available and the school children can actually handle it?
Well, first of all, is chlorophyll toxic? Yeah. So I showed you a dye. This is almost exactly the same structure. I think there may be some, there may be some misunderstanding. We have been asked by our industrial partners and licensees to test every dye we promote as for practical applications like the ones you saw in the flexible cells. They have been tested as to the biological harmlessness and biocompatibility. We have done toxicity tests. We have done also tests whether these dyes are mutagenic or carcinogenic. And so that costs actually a lot of effort and a lot of money from us. And we have published some of these tests. So we're very careful in selecting compounds. I should mention to you that at one time I had an industrial partner. He was a simple glass maker, and he started making those glass cells. And one day he said to me, "Professor, I want to make sure that there's nothing toxic. I don't want my dog to suffer from your compound, so please promise that your dog won't suffer. These are harmless compounds." So some other competing technologies use very toxic materials like the cadmium telluride, or some of the dopants in silicon are very toxic. So we are very careful about environmental compatibility, and so the dyes at the end, well, I must mention to you that a week ago we had another visit from a parliamentary commission in Lausanne, and I made a cell out of hibiscus tea. And to show that it was harmless, I drank out of the same glass we put the cell in to sensitize it. And so I can do that in front of you, and I won't be afraid to be intoxicated. Thank you for your comment.
Thank you.
Anybody else? There's one more.
Thank you. I'd like to ask about the electrical connection to your cells and how that differs from the more traditional cells. It looked quite simple from what I could see from your slides, but I'd just like you to explain a little more how that happens.
Yeah, so as you know, in the PV field, there are several approaches. Thin film, they put very often in series, they have those stripes and in series connection. When you have large surfaces like we have, the glass is not conductive enough. Even though there is a transparent conducting layer on it, it's by far not conductive enough to be able to collect that electricity. So we have to resort to either use some collector grid, like the silicon PV does. That's why the efficiencies come down. they come down by, say, 10 to 20% because you lose that active area by the collector grid. Or else you do this in series connection. And actually, a beautiful example of combination of both is that module I showed you from Fraunhofer. You see that yellow, that big module, the one that has a record size for screen printed. That actually has cells. You don't see it. It's a meander type collector. It's a very nice, a beautiful concept to get the current collected and still have aesthetic appeal. And so you have to do that. You have to. And then the question is, it was your question how I put the modules in series, or was it how to make a big module out of a small cell?
It was basically how to collect the electrical.
Yeah, that's a good point, and I think I addressed that question. So you have to be very careful about that.
Okay, we have two, perhaps these should be the last ones, two questions from the internet audience, or two comments. Three, how would you make these clear? I think he's talking about the panels, clear, and the influence of part shading on efficiency, and is this technology especially suitable to combine PV and solar thermal in a single panel? So there's three little...
Yeah, absolutely. It's something we have in mind. I'm now addressing the first question, the combination of PV and solar thermal. It's an excellent suggestion because, after all, the efficiencies look reasonable with regards to competition, but if I say you get 12%, that's still 88% is lost, and that's mainly due to the infrared part of the solar spectrum. So heat is generated, and that should be collected. And so to combine the Dyson-sized mesoscopic solar cells with a heat collect is particularly suited because we have the transparency. We can have the longer wavelengths go through the cell and, say, be concentrated or use just a water heater. So that question is a very good suggestion, and we're actually writing a proposal that would address this very point at the moment.
Perhaps we better stop the incoming messages because they're piling up here.
Wow, another hour. Yes, well, can I just answer one question that is the ruthenium? Yes, ruthenium, this analysis has been made that although ruthenium is rare, it's true, but there's very little used. We typically use about 100 milligrams of ruthenium per square meter, and so that's, from the cost, is actually a very small contribution. And availability is also not an issue. There are thousands of tons of ruthenium stockpiled, and so the terawatt scale that has been shown can be reached even with ruthenium dyes. But as I showed you, the new dyes, they use other zinc and other elements. Thank you for the question.
So that's, you've got 1 minute more if you can.
Okay.
Do a bit of,
influence of
money's worth, you know.
yes, fine. I could go on for the whole morning. Influence of partly shading. Yes, it's this is a very, very important question. The cells are forgiving in the sense that when you go into reverse bias, I think that's what the person who asked that question must be concerned about, shading driving the shaded cell in reverse bias. There is an opening, like having a built-in diode that releases current. And so you don't necessarily need to have reverse bias diodes to protect the device against shading. It's alleviated by this by the current release under reverse bias of the cell itself. Unfortunately, I don't have the time to go into details, technical details. Thank you for your question.
Okay, thank you very, very much. You've been a very good sport answering these.